Hi, welcome to my channel JaberTime. Today I'm going to go over the mean absolute deviation. The formula is written as you could see in the front slide. Mean absolute deviation, MAD or MAD, is the distances away from the mean being summed divided by n. It's the average of the distances away from the mean. Let's get into it and look at the definition in words. So the mean absolute deviation of a data set is the average distance between each data point and the mean. The larger the mean absolute deviation, the greater variability there is in the data. In short, the data is more spread out. I'm going to show you enough examples. Hopefully this idea is going to be so clear. Here's example number 1. I have 10 numbers, and the numbers are 12, 10, 10, 8, 11, 4, 10, 14, 12, 9. They're not in order. We need to find the sum. We need to find the mean, divide the sum by 10 numbers, and put it right there. If you take the difference from the mean, because they're going to be to the right and left, they're going to add up to 0, always. That's why we take the absolute value, because we want the average distances away from the mean. So, once you do the math, I'm saving you some time here, you add them up, and the sum is 100. Divide by 10, because there's 10 numbers, and you get 10. X bar, or the average or the mean, is 10. 12 minus 10 is 2. 10 minus 10 is 0. 10 minus 10 is 0. 8 minus 10 is negative 2. 11 minus 10 is 1. You just keep doing it, and if you add them up, it's a 0. It has to be 0. Because the mean is balancing the numbers to the right and left. If you get more numbers on the right, it's going to have to move to the right a little bit. So, we talked about this in class, and I think it's clear that the average has to be in the middle, like 70, 75, and 80. The average has to be 75. If you get another score, a fourth score, and it's like 90, your average is not going to be 75 anymore. It's going to move up. So, the absolute value of the distances away from the mean, 2 will be 2, 0 will stay 0, negative 2 will be positive 2 now. Negative 6 will be positive 6. If you add those, it's 18. 18 divided by 10. I'm now averaging not the numbers themselves, the distances away from the mean. I call it distances because they are positive numbers now. And it's 1.8. That means it's like if you display them on a number line, on average, every single data is about 1.8 units away from the mean, to the right and to the left. Here's another example. 7, 14 all the way down to 8, and one more time, they're not in order, so we do the math, we add them up and divide by 10, still 10 to make it easy. The sum is 100. Divide by 10 is 10, so the mean is still 10. So the mean in this case is not helping much. The data are not spread the same way, so I cannot tell from the mean how far they are apart and so on. So we need more measurements besides the mean, the median, the range, and so on. The mean absolute deviation is when you add the positives, the distances. Now it's 28. 28 divided by 10 is 2.8. Let's go back to the first problem. The first problem has 1.8. So these are closer to the mean. And these numbers in form B, or example number 2, are within a longer distance, 2.8 instead of 1.8 on average. What do I mean by this? I mean, the table does not help you maybe much. Maybe I'll do it differently and I'll show you what do I mean in a different view, instead of just looking at tables and numbers. This is form A that we looked at earlier, and mean absolute deviation was 1.8. This is form B, and the mean absolute deviation was 2.8. If you look at the data right here, This is more spread. This is more centered. And usually the mean is like a central data. They tend to be in the center. So that's more spread, higher mean absolute deviation. The formula is the averages away from the mean as distances. Absolute value means distance. Don't keep it negative. Now look at the data and compare them. These are 10 numbers. These are 10 numbers. The average is here 10. The average here is 10. Not only that, the median is in the middle, which is still 10 here. The median between 9 and 11 is still 10. The range is 14 minus 4. If you put them in order, 10. The range here is still 14 minus 4, which is 10. So without looking at the data, if you don't see the table, and you look at these measurements and calculations, you go like, oh, it looks like they are identical. Both data sets A and B are identical. Not exactly. The mean absolute deviation here is 1.8. The mean absolute deviation here is 2.8. So this one is more spread. This one is more centered or closer to the mean, the center. I'm going to have more examples, so let's move on. Here's Form C, still 10 numbers. Now this time I'm putting the numbers in order, so you could see the pattern and see how it goes. 2, 3, 3, 5, 5, 5, 7, 8, 9, 13. If you do the math and you add them up, I have 60 as a sum. And when you finish the math, 60 divided by 10 is 6 for the average. 2 minus 6 is negative 4. It's all done for you guys. The distances are 26. I have 10 numbers. 26 divided by 10 is 2.6. Here's another example. By the way, if you feel like I'm going too fast, just hit the space bar to stop it. And when you hit the space bar again, it will play again. Here's my other example. 2, 2, 2, 2, 5, 5, 5, 11, 13, 13. If you notice, I'm trying to put some numbers right here that they are far apart. The 2s are all the way down on the number line. The 13 and 11 are all the way up. So this is like more spread. Okay? If you do the math, you still have the average of 6. I played the game to make it same average, same mean. But look at the mean absolute deviation. On average, how far the numbers are away from the mean. 3.8. The sum here is 38, where in the previous one it was 26. That's a big difference. These are more spread as like evenly, let's say right and left. But this one is on average, they're apart, away from the mean, more than the mean. The mean was 6. 6 is right here somewhere. This is too far below. This is too far above. That's why they gave it a more average distance away from the mean. Okay. More examples. This time I'm going to have less numbers. Only 5 numbers. 0, 10, 20, 30, 40. So if you make a number line, that's like, you know, exactly distributed. If you add them up, the sum is 100. Divide by 5, it's 20 as an average. 40 minus 20 is 20. 30 minus 20 is 10, and so on. This will add up to 0. You take the averages or the sum of the distances away from the mean, which is the absolute value. I get a sum of 60. 60 divided by 5 is 12. Alright? Let's take another example of the same size, and you'll see what do I mean. See, these are 10 and 30 are close to 20, which is my average. In my next example, here we go. Look, 1 is farther from 20 and 39 is away farther from 20 compared to the previous examples. Look at the previous example. 10 is down below 20 by 10. 30 is above 20 by 10. Where in this example, it's down from 20 by 19. Down by 19. This one is above 20, the mean, by 19. So this is going to have a higher mean absolute deviation. Let's go back. The mean absolute deviation is 12. On the one here that I said they are far away from the mean compared to the first example, it's 15.6. That's higher. Okay. Now, these two last examples with less numbers, I'm doing it as a graph to show you and with more detail. It's a lot of detail, but as I said, you could pause the video by hitting the spacebar and read more. Take a look. The way these numbers they look like this: 10, 0, 10, 20, 30, 40. These numbers, they go like 0, 1, 20, 39, 40. They still have the same average, the same median, the same range, the same average or the same mean. They're all the same, 20 and 40. And the mean here is 20. The mean here is 20. But the distances away from the mean on average, which one is higher? This has a 12. This has a 15.6. 15.6 is higher. You could see that distances are more on average than the distances right here. It is too far apart from the mean to the left and away also to the right. These ones are kind of like balanced, a little bit balanced compared to this one. So this one has a mean absolute deviation of 15.6. This has a mean absolute deviation of 12. And that says it all. When you have the mean absolute deviation, or MAD, is more, that means the data are, on average, are farther from the mean. All right, I'm gonna add another example. See this part here, right here? I want to make it more detailed. I'm gonna go on top of Form E and add more to it. Instead of comparing it to Form F, here's what I mean. Here's Form E. We did this and we talked about it. It's 12 on average as distances away from the mean. Let's take a look. If I have numbers as 8, 8, 20, 32, 32, the distance here on average is 12. So if you go right 12 and right 12 and left 12 and left 12, of course it's going to have a 0. If you do the math, this right here, the median is 20, just like that. The range is 24. Here the range was what? 40. This has less range. The mean absolute deviation is 9.6, which is smaller. Notice that 9.6 is less than 12. Because here, you could see the picture, it's like farther on our number line. If you are graphing this by hand, and you want to use a ruler to graph the line, this line, if you do that on the same paper, is longer than this line. So these data are farther away, more spread on average compared to these numbers. Okay, it's just an idea to show you that what does 12 means. Kind of like you're not too far away, you're not too close to like 10, 20, 10, 20 here. No, they're all about like 12, except this guy right here. The 12 is not away from, sorry, the 20 is not away from 20 by 12. So it's just an idea, okay? So the 9.6 for these numbers is the average. Why it's lower than 12? Because 0 is one of the distances. It's one of my data, 20. It's going to add up to the table. So I have 20, 12, and 12, and 12, and 12, and 0. Divide by 5, and that's the reason why. Okay, that should do it. And thank you for watching, and I'll see you in the next one. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.